The reaction we are talking about today is a single displacement reaction. So a reminder about what that means. In a single displacement reaction, you start out with an ionic compound and something that is by itself. So looking up here, which of these is the ionic compound and which of these is something that's by itself? Raise your hand. All right, what do we got, Brady?
The ionic compound is the water, and then OH, or that's the water. And then the metal by itself is sodium metal.
Yep. So we've got sodium metal, that's just something by itself. Remember, metals are allowed to be by themselves because they can do metallic bonds. Just a heads up, Tuesday and Wednesday of next week is when we are having our chemistry assessment. So one of the things that you're going to be expected to be able to do on that chemistry assessment is look at some molecules and say, oh, do these have metallic bonds holding them together? Do these have ionic bonds holding them together? Or do they have covalent bonds holding them together? So be prepared for that. So, in a single displacement reaction, you have an ionic compound, and then you have something by itself. And in this case, yes.
What's a covalent bond again?
A covalent bond is when they are sharing the electrons instead of stealing electrons. So covalent bonds are usually going to happen between two or more nonmetals, while ionic bonds are going to be happening between a metal and a nonmetal. With a few exceptions like hydrogen, which can act sort of like a metal because it forms cations, which are positive. All right. So, when it comes to these reactions, first thing we want to acknowledge is why it happens, right? Why is there going to be a chemical reaction in the first place? And the reason why here is because sodium is more reactive than hydrogen is. And this should make sense if we think about it. If you think about what a hydrogen atom looks like compared to a sodium atom, hydrogen just has this one proton, a single electron shell, and one electron. When it forms an ion, it loses that electron, but that electron's in pretty close to the nucleus, so it's held pretty tightly. Compare that to sodium, which has its 11 protons and 12 neutrons. It has not one, but 3 electron shells. So we've got 8 electrons in that second shell, and just 1 electron in that outermost shell. This 1 electron is held a lot less tightly than this one is. So it's a lot easier for sodium to form a cation than it is for hydrogen to form a cation. Does that make sense why that's the case? Right? This electron is farther away from the thing that's attracting it than this one is. This one's more tightly held. That one's less tightly held. This makes sodium more reactive overall. Yes?
So it's like how if you have like a spaceship, it's a lot easier to like blast meters when you're way out in space than when you're down.
Yes, exactly. Yep.
I have just another question about covalent bonds. How do you know the difference between ionic bonds and covalent bonds?
The way you would tell the difference between an ionic bond and a covalent bond is a covalent bond is going to contain 2 nonmetals. It's going to be between 2 nonmetals, which are typically on the right-hand side of the periodic table. The ionic bond is going to have a metal and a nonmetal, because metals form cations, which are positive, and nonmetals form anions. So you need to have one of each to do an ionic.
What's a metallic? It's like
A metallic bond, you're just going to have a metal. So like, why is it that I can have just like a hunk of iron, and that's perfectly stable on its own? Well, because metallic bonds. So like, sodium on its own is stable. Or you can just have sodium. You can't have just a single hydrogen atom by
So
itself.
then why doesn't it react?
What's that?
If it's like if it's stable on its own, then why does it want it? Why doesn't it want this way?
Because it's more reactive than the hydrogen. So basically, only if it's got access to the hydrogen hydroxide is it going to want to do this place. Yeah. Yes. I'm sorry, I thought you reached your hand. Okay. So this is a single displacement reaction. We're going to predict the products. So the first thing I'm going to say is sodium more like the hydrogen or more like the hydroxide?
Hydrogen.
Why is it more like the hydrogen, Calder?
Because it's gonna take the place of the cation.
Yeah, it's capable of forming cations, like hydrogen. Both these things form +1 cations. So the first thing that's going to happen is the sodium is going to take the form sodium hydroxide.
And OH can be best.
And then the hydrogen's left on its own, right?
And then the hydrogen's left on its own, but is
No.
a single hydrogen atom stable?
Hydrogen
No.
gas.
Yeah, we gotta make hydrogen gas, so that's H2.
So then you make 2 sodiums.
Yeah, okay, so y'all are getting ahead. Yes, we do need to balance this, because this is currently not balanced, so in your notes, I do want you to go ahead, take a moment, and balance these equations. And if you want to just pause the video, so you
Good job.
Okay, so first up, we want to do our counts. We're going to do this all together. How many hydrogens on the left-hand side? Remember, I'm counting hydrogen separate from the hydroxide.
1,
Excellent. And on the right?
2,
So there's our first thing that's going to be out of whack. How many hydroxides on the left?
1,
Nice. Hydroxides on the right?
1,
One hydroxide on either side, so that's so far balanced. Sodium's on the left?
1,
Sodium's on the right?
1.
Okay, so we've only got one thing out of whack. It is our hydrogens. Raise your hand if you can tell me how we're going to get to 2 hydrogens on the left-hand side. Marifa.
2, and so you'll have 2 HOH molecules.
Absolutely. We will have a second water molecule. And doing so is going to give us 2 hydrogens, but it's also going to give us 2 hydroxides. So now our hydroxides are out of balance. Calder, how are we going to balance that?
Put 2 on the sodium hydroxide.
Absolutely. Let's have a second molecule of sodium hydroxide. That will give us 2 hydroxides, but it also gives us 2 sodiums. So how are we going to fix the sodiums?
Put a 2 on the left side.
The left side of what?
A sodium.
Yeah, we'll have a second molecule of sodium metal here, and that will get us to 2 sodiums. So now we have balanced this chemical equation.
Yay.
So let's talk about a few other things to deal with this. One of the skills that you're going to be expected to have on your assessment on Tuesday is I want you to be ready to tell apart certain types of chemicals. I want you to be able to tell the difference just by looking at the formula between an acid, a base, and a salt. Acid, base, also hydrocarbons. And
See.
based on a description, you should be able to tell whether something is a
Oh,
indicator.
that's right, that's right, that's right.
So looking at this, acid, base, salt, hydrocarbon, indicator,
Show.
what is sodium hydroxide? Which of those things is that? Raise your hand if you can tell me. Is sodium hydroxide going to be an acid, a base, a salt,
A base.
hydrocarbon?
A base.
It is a base. How do we know it's a base?
Because OH, you're adding an OH without adding a hydrogen.
Bingo! The presence of that hydroxide anion, without having a hydrogen to go with it, that's what makes this a base.
Is the test open notes?
Absolutely. And just a reminder about the way I do things, it's not going to be like it will be a test-like experience when you're taking it,
Yeah.
but a reminder that not only are you going to be able to do retakes, the expectation is that everyone's going to fix it up to 100% because I want everyone to master all of this material. I think it's all important.
It's just we can use every single note sheet,
Every
or
single
can we
note
just
you've got.
only have to put on one note?
Um,
So we can use all our note
you
sheets?
can bring your whole binder full.
Oh, nice.
Absolutely.
Okay.
You just can't use your phones. Yes, Amy?
Can you go over what a hydrocarbon is? Is it just a hydrogen and a carbon?
So it is a molecule that contains hydrogens, carbons, and optionally oxygen. Doesn't have to include oxygen.
Then
So something like CH4, methane, that's a hydrocarbon because it's got carbon and hydrogen. Something like C6H12O6, glucose, that's a hydrocarbon because it's got hydrogen, carbon, and oxygen. Yes,
And those are necessary for combustion reactions, right?
those are necessary for combustion.
but then you have to add oxygen gas.
You have to add oxygen gas. Right, remember, oxygen gas has this really cool property of when those double bonds break, they release a lot of energy. So really exothermic reactions from oxygen gas. Yes.
And can you have anything else in a hydrocarbon, or can it only?
Only hydrogen, carbon, and oxygen, and the oxygen is optional.
Because I get it, because you need the carbon and the hydrogen for the carbon dioxide and the water, and then if you can have more oxygen to make more carbon dioxide or more water, but it's not necessary because you have the extra carbon, the extra oxygen gas.
Yep, exactly right. All right, so we're going to take a moment and pause and talk about safety here because there is going to be a minor explosion later on today, and people will oftentimes assume that the thing they need to worry about is like the heat or like explosion parts, but that's not actually the most dangerous part about this chemical reaction. The most dangerous part of this chemical reaction is this stuff, the sodium hydroxide. Bases, and this is a strong base, are really caustic to people, right? They are capable of reacting with fatty tissue in your skin and giving you pretty nasty chemical burns. So the first thing I want to make clear is that under no circumstances are you going to touch any of the bases. You're not going to touch the sodium metal. I'm not going to touch the sodium metal. I'm going to handle it really carefully to make sure it never touches my skin. The water in the bucket, once sodium metal has entered that water, that's a hazard. We're not going to touch it because the sodium hydroxide is dangerous for people. Yes?
Last time we did it, is this the thing where there's like the big tub of water? It's not just that little.
No.
Okay, good.
There's a bucket back there. The blue
It's like one of
bucket.
those Home Depot buckets.
It's a little small, just a little blue bucket. So, you can see it by the sink. That's the first thing I want to say, is that the water is actually going to be the dangerous part, because there's going to be a small explosion eventually. Some of that water might splash out of the bucket. Is everyone wearing closed-toed shoes?
Yes.
Great. So everyone's wearing closed-toed shoes. Just make sure that you're not dipping your toes in anything caustic. The next thing I want to talk about in terms of safety, if this shouldn't happen, because we're all going to follow clear safety things. You're not going to stick your hand in the water bucket, because I just told you that it's perilous. But if you were ever to come into physical contact with the sodium metal or with sodium hydroxide dissolved in water, then there's a few things we're going to do. One, if you've got a solid on you, first we're going to brush that solid off into the trash, as opposed to directly running it underwater, because remember, it reacts with water, so you're not going to go straight to water. Okay? When it comes to the sodium hydroxide, if you were to get splashed by that bucket, we don't want the sodium hydroxide to react with your flesh, so instead we want to give it something else to react with. What do bases love to react with? Lemons, acids, right? You will notice in the back of the room there is a big old jug of vinegar.
Oh, okay.
That jug of vinegar is so that if you have any contact with that caustic water, you're going to be able to wash your hands with that rather than with straight water. Okay? Make sense? Okay, so that's 2 bits of safety information we're going to bear in mind. Now this reaction is a little bit exothermic, but it's not very impressive, right? This part right here, basically when I stick the sodium metal in the bucket of water, the water will become caustic, but we're not going to notice that because you're not going to be standing right next to it. There's no indicator in the bucket that would let you show off the color, right? Because we're not going to be looking at it. And hydrogen gas, it's invisible, but it's just a gas, right? If you listen, you might hear a hissing noise, very faint hissing noise, as that hydrogen gas bubbles up out of the water and into the air. You might be able to see a little bit of the gas, right? So that is a possibility. So this part, not going to be terribly exciting to start with. It is exothermic, but only a little bit exothermic. It'll give off a tiny bit of heat, but not a ton. Which brings us to our next reaction. So in our next reaction, we have that hydrogen gas, which hopefully is accumulating in the bucket. We've got this hydrogen gas. What was that other gas that is really reactive and releases a lot of energy?
Oxygen gas.
Oxygen gas. Is there oxygen gas around?
Yes.
Yeah, oxygen gas
I'm breathing it in right now.
is a solid 21% of our atmosphere. So we've got oxygen gas, and that's just in the air nearby. Now, oxygen gas and hydrogen gas are capable of a really fun synthesis reaction. Has anyone ever heard of something called the Hindenburg? The phrase, "Oh, the humanity" might come to mind.
Oh,
Yeah.
humanity.
What was the
I read an I Survived book on that. When I was in like 4th grade.
There you go.
So the Hindenburg was a blimp, and its envelope, right, the balloon part, was full of hydrogen gas. Yeah. So the envelope was full of hydrogen gas, and it had a little leak. And then there was a little bit of a spark, and it reacted with oxygen from the atmosphere, and it exploded.
That must have been a huge explosion.
It was a massive explosion. Everybody on it died in a ball of fiery death. It was very bad. I mean, to be fair, they were all Nazis, so like it's not that sad. I don't know much about the Iron
Where was it going to again?
I think it was heading from Nazi Germany to the U.S.
Yeah.
And there's
I don't know much about
Wait,
the
what's
details.
it? What were they in?
I don't
Wait,
know.
what were
I
they
think it
in?
was pre-war.
There's a blimp.
What's that?
But I don't actually know.
The
if
huge
you know, like,
balloon
travel,
things
so I
that
don't
fly
wanna
to
give
the
too much
sky.
detail, 'cause I
Oh,
might-
that one?
You know, like in
Yeah.
Yeah, that's a blimp.
Oh,
Wait, no,
oh that
that's
thing's
right.
huge.
Yeah.
Blimps are huge.
There's
Oh,
only
wow.
actually a few blimps in existence, by the way, like single digits numbers of blimps on the planet, which is kind of wild.
And but it goes so much.
air blimp.
Does it go so much?
Yeah, but there's not many of them.
Does it go so much slower than planes?
They're very simple. Yeah. All right.
Isn't there also Zeppelin?
Zeppelin is another word for blimp.
Oh.
It's the same thing.
All right. Owen, y'all. So, when hydrogen gas and oxygen gas react with one another, they create a compound. And the compound they make, this is going to be a synthesis reaction. And they actually are making, you know it, you love it, H2O.
Water.
They're literally just making water. But
Where's the oxygen?
because this is a reaction with oxygen gas, we're also giving off.
Rocket fuel. This is rocket fuel, right?
That's what this is. Yeah. We're also giving off a lot of heat. So when we have this exothermic reaction, there's going to be a few ways that you're going to be able to tell that this reaction is giving off energy. You might see a very brief flash of light, especially if you go in slow motion. Maybe not, but you might be able to see the fire. There will be heat, but you're going to be too far back to feel the heat. You will probably notice it most through the sound. Because as this happens, we're creating a lot of hot gas that is going to expand outwards really fast. That's a sound wave, right? It's gas moving, motion in gases. So we're creating a pretty sizable sound wave that you're going to be able to notice. So that's how you will be able to tell if this is an exothermic reaction. You will be able to see the water vapors. There will be a cloud. People oftentimes are a little like, oh, what's that stuff that came off this big chemical reaction? Is that dangerous? That part's not dangerous. That's literally just a
There's
cloud.
a
It's
mushroom
water vapor,
cloud.
right? That we're creating after this explosive synthesis of water. Yes.
Is that heat the one that's doing the stuff?
This second one is going to be the one that is the explosion.
But like, is the heat that came, is it plus heat under NA?
Yeah, this one makes a tiny bit of heat. It's basically just enough heat to serve as the spark
Okay.
that's going to allow these two to react.
I want to do this at home.
No.
This is fun.
I'm going to do this under supervision for y'all now in class. All right,
hey,
so
guys.
here's a question. Is this balanced?
No.
No, this is not balanced. I want you to take a moment, go ahead and balance it. If you can do a favor and pause the video.
Sure.
And oxygen, we start with 2 of each on the left, 2 hydrogens and only 1
Balance.
oxygen on the right. So we need to have a second oxygen on the right. How am I going to make that happen? Oh, did you restart filming? Great.
You put a 2 in front of the H2O.
All right, so we're going to have a second water molecule. That will bring us up to 4, 2 times 2 hydrogens, and 2 oxygens. So now we've got 4 hydrogens on the right, but only 2 on the left. How am I going to make there be enough hydrogens on the left-hand side? Yes? Yeah, we'll have 2 molecules of hydrogen gas. So that brings me to 4 hydrogens on the left-hand side, and now we're balanced. 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. So this is the chemical reaction we're going to do. And this is the one that's releasing all that heat and energy. Now, a few things to note about safety. I am going to be the only one who touches any of the materials. Everything on this tray I want you to never touch. Just don't touch them, don't mess with them. You will notice I have set myself up today wearing clothes that cover most of my body. That's basically to make sure that if there's any debris or things flying off, it doesn't hit my bare skin. Because I'm the only one who's going to be anywhere near close to this. Everyone else is going to be plenty far away. I will show you how far back you have to be for this. Additionally, because our eyes are very vulnerable, I am going to wear goggles. I am going to be wearing goggles for this. And in order to keep it from touching my hands, I am going to be wearing gloves. When we finish class, I will show you how to properly and safely dispose of gloves that might have been in contact with hazardous materials. So for y'all, the most important part of this is going to be that you keep your distance. So I will show you how far back you need to be. The first time we do it, you're going to be able to, I just want you to watch with your eyes. Second time, if you want to film it, I will permit that. Okay. So, we are going to head inside.
Woohoo!
Field trip. It's just a single piece of sodium.
Mad
We're going to wait till
scientist.
Trevor is back. Hi, if you want to, we're about to do an experiment. I just need you to scooch a little bit farther back. Behind the blue poles. There you go. All right, y'all ready?
Yes, sir.
Yeah. Here we go.
Yes, sir. Yeah. Why can't I say yes, sir?
Yes, sir, is everybody's accurate. It's just me. All right, that was with one piece of sodium.
One piece of sodium.
One piece of sodium. Go.
Let's go. I'm excited.